Okay, hi everyone. So welcome to lecture 5 in this series. So today we're moving really properly into the assessment of peripheral insulin sensitivity and insulin sensitivity and readouts in general. So we're now no longer really focusing on the causes of obesity at all. So we're going to look at the consequences of it, and in particular, how obesity and insulin resistance or obesity-induced insulin resistance can be assessed in mice. So today I'm going to talk about fasting and fed measures of metabolites and how they relate to metabolic health. Then we're going to move through to GTTs and ITTs. Then we're going to run into euglycemic hyperinsulinic clamping. And the idea there is what we're going to do is we are going to talk about how the clamp works, what it does, and also some of the benefits and advantages of clamps over things like GTTs and ITTs. And then we are going to do a couple of small sections where we talk about lipid tolerance tests, and finally, acute insulin stimulation for phosphoprotein analysis in the wet. So a range of techniques you can use to see whether your mouse is healthy or sick, in particular from an insulin sensitivity point of view. So why are we interested in this and what are we looking at? So the natural history of type 2 diabetes is a graph many of you will have seen before. And essentially, it is thought that as time progresses, the first major stage as you move towards type 2 diabetes is the buildup of insulin resistance. And this insulin resistance will be okay so long as you can continue to produce insulin. But at some point, you will go into the process of beta cell failure. You will stop producing enough insulin. And at this point, it's when we start to see blood glucose rising higher and higher, and we get frank diabetes. Now, the area that I have worked on and our lab works on predominantly has been this area here, at a point where beta cells are still functional, but we have insulin resistance, and therefore we're interested in looking at how to assess how insulin resistant our animals are. So what does insulin do in terms of carbohydrate and lipid metabolism in different organs? The answer to this is obviously many, many, many things. And, you know, this is not a topic for one talk. There are multiple international conferences per year on this question. However, most of the tests we're doing in vivo are based on assessing specific aspects of insulin's action. And so they are as follows. So the action we're usually looking at with respect to muscle is the ability of insulin to promote glucose uptake to muscle. And insulin resistance is characterized by a reduced ability of muscle to take up glucose for the same dose of insulin. In terms of liver's function that we are most often interested in when we do metabolic tests in vivo is its ability to suppress glucose production from the liver. So, and insulin resistance is characterized by a failure to suppress glucose production. There are other things we can measure, but I would say this is the most common one that we're measuring when we're doing in vivo metabolic tests on rodents. And finally, in terms of adipose tissue, insulin is very important in adipose tissue to suppress the release of free fatty acids. And insulin resistance is characterized by a failure to suppress free fatty acids. So these, I would say, are the sort of three most canonical readouts of insulin action on the different organs. And so we should keep these in mind as we go through the tests. Okay, the first thing I'm going to show is just simply some data that we have from a mouse line that I've been working on, which is the fasting and fed metabolite levels and using them as a readout of metabolic health. And so in this particular line, we have measured glucose and we have measured insulin. And in the fed state, we can see that glucose between the wild types and the knockouts, blue wild type, orange knockout, is the same. However, in order to maintain that same level of blood glucose, the knockouts require about 3 times more insulin. So by definition, they are insulin resistant. Because you have 3 times as much insulin, it's not causing this glucose to fall to nothing or to reduce in levels. It is this additional insulin that is required to maintain blood glucose at the same level as the wild types. Now, the really cool thing about this line is we see quite the opposite in the fasted state. So in the fasted state, we actually now find we have lower blood glucose and formerly similar, but a tendency to lower insulin levels. And we can combine insulin and glucose levels in order to get a bit more of a picture of what's going on. So this is the principle of HOMA-IR, which is done on fasted. And what you essentially do is you multiply glucose by insulin by a constant to get HOMA-IR. But we can do it in the fed state just as well. And this makes an important point. So if we multiply glucose by insulin, we get a rather spectacular unit here of millimoles per microgram per liter. And what you can see is, oh, sorry, that should be times. What you can see here is, yes, we see the same pattern we had before, an improvement in the orange mice versus the blue mice in the fasted state, and a worsening in the fed state, but you can just see the spectacular difference in magnitude. So it is possible to have these divergent results, and it's also important to realize just how big a differential you may see between the fed and fasted state in terms of the amounts of glucose and insulin combined. So I'd say that the kind of key conclusions from these are, we know from this data that there is something going on in our mouse, so it's an excellent and it's a simple readout of the metabolic status of our mouse. I would argue based on this data, it's really important to consider both the fed and fasted states. It's easy to get trapped into just doing one or another, but you can see in this case, we have the most extreme example you can get, which is literally diametrically opposite phenotypes depending on whether the animal is fed or fasted. They're actually quite powerful variables because they represent, in a sense, a physiological state, particularly the fed state. If you take your mouse out of its home cage where it's been living, you've not done any interventions to it, you're going to get what's happening in that mouse at the time. Obviously, it's only a snapshot, but if you then also do these analyses on serum you've harvested either immediately before or even post-mortem, it may be also relatable to the tissues that you've harvested. So you could look at how gene expression associates with a serum metabolite, and that can also be powerful. The downside of these is they are not particularly informative in terms of which organs are responsible for causing that hyperinsulinemia or causing that hypoglycemia that we saw in our orange mice versus our blue mice. So it's essentially an overall indicator of metabolic health, but it's very useful because it's very quick and it's very easy. Okay, next we're going to move on to GTTs. So the first thing I'm going to say up front is GTTs are an incredibly complicated test and an incredibly complicated variable. And I'm going to try and convince you of it by the end. It is, I would argue, the most common metabolic test in neurometabolic research. And this is a slightly old slide. I think this was probably true several years ago, that the IPGTT as an intraperitoneal, so injected into the peritoneum of the mouse with 1 gram per kilo of glucose, was the most common. I think in part because the IMPC pipelines, which have tested literally thousands of lines of mice, I believe that they use 2 grams per kilo of oral glucose delivery, so gavage. That's probably now, I would say, overtaking the 1 gram per kilo IPGTT test. So why is it so popular? So it has a wide acceptance in the literature. You'll see it in most papers, I would argue, where people have done neurometabolic phenotyping, looking at insulin sensitivity, diabetes. It's been used for many, many years. It's very easy to do. It's amenable to moderate to high throughput. You can do 20 of them in a day, relatively straightforwardly. It's very easy to standardize your protocol and your workflow. You can have the same steps. Glucose, it's easy to get hold of. So I think it's quite an easy assay to standardize. Potential issues with it is heavily susceptible to batch effects, and we'll look at those. I'm not going to show you the data, but it's heavily susceptible to user bias because stress can affect glucose levels. So if you have an experienced user who's good at handling mice versus an inexperienced user who's nervous about handling mice, you will actually find a bigger glucose tolerance curve for the inexperienced user because you are stressing the mice. It's also a compound test where many different factors such as beta cell function, liver insulin sensitivity, muscle insulin sensitivity, all can potentially input into your readout, which will be glucose or potentially glucose and insulin levels in the blood of the animal at different times. So it's quite difficult to interpret from that point of view. How did we get to it? So this is a really odd question. I'm not really sure why we do it in mice. The GTT was first devised for the detection of beta cell failure in humans. There were two schools of clinicians. One lot thought 50 grams of glucose orally was the correct test. A second lot thought 100 grams of glucose orally was the correct test, and they compromised on 75 grams of glucose. There's no scaling in the human GTT. You do 75 grams of glucose, regardless of whether the person weighs 50 kilos or 200 kilos. Now, an average human in England, however, weighs around 77 kilos, and that was back in 2010. It's probably a bit higher now. So on average, the GTT in humans is actually about 1 gram per kilo. However, I would argue that the human 1 gram per kilo oral GTT is a completely different test to what we're doing in the mice, and we'll see why that is as we go through the rest of this section. Okay, so fasting. Most often GTTs are conducted in the fasted state, and I'm not sure that is necessary in mice, and it may even be disadvantaged. Overnight fasting has to be done in humans because it allows control over food choice. So a person who has eaten a McDonald's for breakfast will have a different glucose production from their gut than an individual who has not eaten breakfast at all. So, and this could make the difference between being diagnosed with diabetes and not being diagnosed with diabetes. So it's clearly something that needs to be controlled for. So does this make sense in mice? Well, the mice are eating exactly the same food every single day, and there is a strong circadian regulation of nutrient utilization. So do we really need to fast the animals? So what does the kind of canonical model of a glucose tolerance test look like? So the idea is you'll have your blood glucose, and then you will put in a glucose load, and the blood glucose will go up and it will come back down. And I would say the sort of generally held view is that in response to this glucose load, you will get an increase in insulin in the blood. And this insulin will be part of the process involved in rectifying the blood glucose. You will have an absorption of glucose, and over a period of time, the glucose will be absorbed, and eventually you will cease having glucose to be absorbed. As a result of this increase in insulin, insulin will do what it's supposed to do to the liver, and that is suppress the production of glucose. So that's insulin's role in the liver, and so you will get a reduction in hepatic glucose output. So this means you will have a liver effect in your model. You'll have a pancreas effect relating to the insulin production. You'll have a gastrointestinal effect. You will have a muscle effect, potentially in the context of the clearance. Kidney effect, because some glucose is going to be produced by the kidney as well as the liver, about 10%, I think is the generally prevailing view. From that GI tract, you may get incretins if your test is oral, and you may also see glucagon production. And then there is a concept called glucose effectiveness, the ability of glucose to promote its own disposal, and that can impact on your GTT. So you can see there's a staggering range of variables. However, I began to wonder whether all of these variables were truly going on when we was doing this study, which I've mentioned before because it's my own work, and that means I can be rude about it if I want to. So the first thing was we did some GTTs, and these were 1 gram per kilo IP GTTs. And one of the things we noticed from these GTTs was we saw absolutely no reduction in endogenous glucose levels during the GTT. So this GTT was done with stable isotopes. We get a nice normal glucose tolerance test. And then we also can therefore, because it's stable, pass it into the exogenous glucose that's been injected, and also the endogenous glucose, the mouse's own glucose. And what you can see is far from going down, along with the model that we saw in our cartoon in the previous slides, the glucose, if anything, goes up slightly, certainly here in this fed state one, which may be related to injection stress, and the injection stress causing the livers to pump out glucose. But it doesn't go down. It remains pretty much flat. There are a couple of other points which are quite nice to mention from this slide. The first is the variation in the glucose tolerance tests between the fasted and the fed state is pretty much identical. It is not the case that conducting a GTT in the fed state has led us to have more variable data. So the argument for fasting being to allow you to reduce your variance by normalizing for whether the mice have recently eaten or not doesn't hold true, at least at the level of glucose. I think the final thing I would point out is we're still seeing exogenous glucose all the way out here at 120 minutes, and we'll come back to that later. But it's notable that the glucose that you've injected may be being absorbed for a very long time. So in addition to not suppressing HTP, I went back and looked at some more data I had, and this is some GTTs I've done probably about 13, 14 years ago now. And we had chow and high-fat diet fed mice, wild type and knockout from this paper. But it's not really the important bit, it's not really the difference in the groups in terms of the glucose, it's the absence of any induction of insulin during the GTT. So the argument that when you inject the glucose, this promotes insulin levels to go up should be measurable. You should be able to see increases of insulin. Again, this is 1 gram per kilo. IPGTT, but we're just not really seeing any alteration in insulin. The offset between these two groups is this is the high-fat diet group at the top, and this is the chow group at the bottom. But the final thing I want to point out here is also the data we had a look at 2 talks ago, which is related to the AKT2 knockout mice. And it was the fact that the AKT2 knockout mice, when we use 1 gram per kilo IPGTT, actually have a normal glucose tolerance test. And although 1 gram per kilo is the lower end of what gets used in the literature, it's still a relatively powerful challenge in terms of glucose levels in blood, because it is more than doubling the fed blood glucose of a wild-type mouse. But in an AKT2 knockout mouse, as we discussed, you don't even get up to the same levels as you see in the fed state. And you apparently have basically a pretty much normal GTT. So what's going on? So if you have no suppression of EGP during a GTT, it would suggest that there's little change in insulin activity during an IPGTT. Equally, no change in insulin during a GTT implies no change in insulin activity during a GTT. And normal glucose levels during a GTT in an AKT2 knockout mouse, this could be caused by hypersecretion of insulin, or it could just imply that the IPGTT is acting independently of insulin, so it doesn't get affected by the lack of AKT2. So we're now going to ask, can a GTT work conceptually with no involvement or increase in insulin activity, where insulin is just not involved? And we're going to call this the simpler glucose tolerance test as opposed to the simple. We're argued that what's going to happen is as follows. We're going to inject some glucose into the peritoneum or orally, GABAergic, and this will cause the glucose to go up simply because we're absorbing glucose. And then over time, the amount of glucose we're absorbing is going to diminish as it gets absorbed and goes into the blood and is disposed to the periphery. And we're going to see no alteration during the whole GTT in hepatic glucose output. And we're going to see no alteration in insulin levels. So to understand how this can possibly happen, we need to consider glucose flux in a mouse. And for that, we need a few numbers. So the first numbers are the blood volume of a mouse. So this is usually defined as being around about 1.8 milliliters for a 30-gram mouse. And the blood glucose concentration of a mouse is about 10 millimoles. So the total blood glucose pool is about 18 micromoles. Is this a lot? Well, probably the answer is no. It really is not a lot of glucose, because the turnover rate of blood glucose at steady state in a conscious fasted mouse is estimated at around 3 micromoles per minute, and that rises to 6 micromoles per minute in the fed state, or the clamped state. You can get a bit higher still. So in other words, mice only have between about 3 to 6 minutes of glucose in their blood. So the blood glucose pool is very small. And that actually is giving us a hint why the GTT in mice may be relatively insulin independent. And that's because insulin has a half-life of around 4 minutes. So if you overproduce insulin as a mouse, you will die before you can get rid of the insulin because you will run out of glucose. So this is just a conceptual idea. It's very different, as we're going to see in a little while, in humans, where the blood glucose pool is at least 10 times bigger in terms of time, at least 30 to 60 minutes of glucose in the blood. So flux equations for a well-mixed pool. This is a really simple formula, but it's important to understand the different sides of the equation. So a pool, in this case, we're talking about is the blood glucose, the amount of glucose in the blood, and that's a pool of glucose molecules. And it will remain at the same size because you have two processes going on. First of all, glucose will be put into the pool, if we're in the fasted state, predominantly by the liver putting out glucose. And the rate of appearance is going to be in units of mass. So there is an absolute amount of glucose being delivered to this pool from the liver. On the other side of the equation, we have the rate of disappearance, and these units are fractional because the glucose that's going to be taken up will be a proportion of the pool. And so if your pool expands, you will continue to take up the same proportion, but that will turn out to be a larger amount of glucose in absolute terms. Okay, so this comes from things like protein turnover equations, where this kind of thing holds true. So the pool size will be defined as the rate of appearance divided by the rate of disappearance. So let's see what those numbers look like in a mouse. Okay, so for glucose, we know the rate of appearance from tracer studies is around 3 micromoles per minute. So it's measured in absolute terms in a fasted, conscious mouse at room temperature. And we know the pool size is around 18 micromoles. So that's 10 millimoles per liter of glucose and 1.8 mils of blood. And so from that, we can calculate the RD as being about 16%, so 0.166. So what happens if the RA halves with no change in RD? So suddenly we drop our glucose production from our liver from 3 micromoles to 1.5 micromoles. It is not the case that the mouse will just become hypoglycemic and die. Instead, what will happen is that the pool size will shrink until 0.166 times the pool size, in this case 9 times 0.166, matches the 1.5 micromoles of the RA. Okay, so often you'll see when you fast them, you halve the blood glucose in some strains of mice, and that's consistent with this idea because the RA drops. Other strains, it doesn't, which suggests some other processes are going on. But the critical point here is you will reset the pool size until the RA matches the RD. Okay, so if we think about then what's going on when we do an IPGTT, we can build a model and we can say, okay, at T0, we're going to stick a load of glucose by using a needle and inject it into our mouse's peritoneum. And that will be a fixed amount. We will know how much we're putting in, and about 180 micromoles is the same number. That glucose will have an absorption rate into the blood. So disappearance from the peritoneum, so it's fractional units of 2% per minute. Because over time, the amount in the peritoneum will drop, and simply the gradient between the blood and the peritoneum will get closer and closer and closer until it matches, and then you'll see no more net transfer of glucose. In the blood itself, we are going to have glucose coming into the blood from a second source to the peritoneum, and that's the liver. But we're making this model not have insulin involved, so we're just going to fix that. We're going to say it doesn't matter we've injected in a load of glucose. We're just going to say the liver is chunking out something like 3 micromoles per minute of glucose. It's just chunking them out. And then the glucose disposal is going to be fractional. It's probably going to be around 20%, but we're going to use our software to solve it. But we're not going to allow that to change either. We're going to say, before we put that glucose into the peritoneum, it's a 17%, say, and we're going to keep it 17% for the whole experiment. And what insulin should formally do in these kind of equations is increase the RD. So insulin on a muscle cell is going to increase the proportion of glucose that is taken up per minute. So we now have a model where we're just saying we have a mouse, it's producing yay amount of glucose from its liver, it's disposing of yay proportion of glucose from its blood each minute. Keep that static. What happens if we suddenly put a load of glucose in the peritoneum and allow it to be absorbed over time? And the question is, does this model, when we build it mathematically, can it fit GTT data? And the answer is yes, it can fit GTT data really well. So it fits pretty well. Now, there's a caveat here. This is by no means publishable, and anyone who does any kind of modeling of GTTs will be horrified looking at this. It's a really underdetermined model. We have too few data points, and also we haven't done this long enough to really get a good feel on the parameters, because at 120 minutes, I already mentioned this briefly, if the turnover rate of blood or the RD of a mouse is around 17 to 20%, that means in 20 minutes, only 1% of the glucose in the mouse's blood will have been there 20 minutes ago. Because each minute you're getting rid of 17% and replacing it with new glucose. So if we're still seeing exogenous glucose, labeled glucose in our mouse at 120 minutes, we're still seeing 1 millimole of it in the blood, that means there was plenty of exogenous glucose there at 110 minutes. Okay? But then, so we would need to extend this until we get the exogenous glucose right down to baseline. But there's another interesting point about our GTTs is we're continuing to absorb glucose over time right throughout the 120 minutes of the GTT. It's not that we suddenly put the bolus in and it disappears. It's going to keep going. Okay. So I would argue that the empirical data we have and also the fact that we can model it would suggest that 1 gram per kilo IPGTT is probably largely independent of insulin. But can we make a GTT at least in part dependent on insulin? And the answer is yes. We can use more glucose than 1 gram per kilo. That's the first thing. And we can perform the test orally, which means we can basically recruit the incretin system and promote insulin release from the pancreas. So here we go. Here's the GTT, and we do it orally, and it's noticeable we have a bit of a sharper downstroke from the peak. Formally, these two GTTs are slightly different. The AOCs are slightly different. But what we're interested in the next slide, and that is insulin. So you can see we go from a fasting insulin of about 0.3 micrograms per liter to 0.4 micrograms per liter, and that jumps up about 4-fold, and then it starts to return down. Now, one of the actions of insulin we can measure a little bit more directly that's independent of our glucose levels, because obviously we pump glucose in, so it's hard to pass that out, is its effect on adipose tissue and suppression of free fatty acids. And this induction of insulin is certainly enough to suppress free fatty acid release from adipose tissue. Okay, and this drug here is actually inhibiting lipolysis, so we start off with lower levels of free fatty acids to start with. So yeah, so it does certainly look like we can induce insulin secretion during our GTTs with a higher dose of glucose, and we can also see that the insulin that's been released is indeed functional. So that's good. I mentioned already GTTs have massive batch effects. So a batch effect, for those who aren't entirely familiar, is the concept that when we do an experiment, we usually care about comparing our two intervention arms. So maybe wild type and knockout mice, treated or control mice. However, there are lots of random sources of variance, and a massive effect is caused by using batches of animals. So we might want to study 8 wild types and 8 knockout mice in total. If we split them into a group of 4 wild types and 4 knockouts, and then another group of 4 wild types and 4 knockouts, and do the same experiment on them, would we expect to get the same thing? Well, we may get the same things. This is showing conceptually what we can see in 2 batches, but it could be offset. So the yellow bars here are higher than the blue bars, and the yellow bars here are the same difference to blue bars, but they have different starting points. So you get different, so you get the whole data set just shift up a bit. And if you just crudely lock all of this together, you'll end up with a non-significant effect, because you can have a huge amount of variance from the controls being here and some of the controls being here. Whereas if you do them all in one batch, you may well find that you get the same sort of variance as an individual batch, but now you preserve your difference in means. And you can correct for this statistically in models, but that's never as good as just having a single batch. And just to show you some actual data, you can see this is a very similar idea. So these batches are significantly different. This is day 1 versus day 2 on some GTTs. The big difference is in the basal. We don't know why, but these ones were at 6 millimoles fasted glucose, and on day 2, they were 11, and they have an equal number of control and treated animals. And you can see that this kicks in through most of the GTT with very significant effect on the AOC. So it's just to warn you when doing GTTs, you've got batch effects. Finally, just to compare how different mice and human GTTs are, this is from a paper from the Mayo Clinic. They had 100 humans, healthy individuals, and they did an oral glucose tolerance test at 75 grams, so about 1 gram per kilo of glucose. And in terms of the glucose levels in the blood, first of all, this is 300 minutes. They're doing it over. Glucose rises about 1.5-fold on average. So you got the 95% confidence interval, so it's very variable. Insulin rose about 10-fold. Furthermore, the insulin remains elevated all the way out till, I would say, at least 180 minutes, and maybe even slightly elevated at 250 over baseline. And that is essentially exactly the same time frame that the glucose remained elevated. When we do our mouse oral GTT, we use twice as much glucose relative to that, 2 grams per kilo. We get a 3-fold induction in glucose, so a bigger spike in glucose, and only a 4-fold peak in insulin. And that insulin has largely returned to baseline. So maybe we could argue this is, I don't know, 50% above baseline, whereas this is 10 times above baseline at 90 minutes. This is by 30 minutes, and by 60 minutes it's falling even lower. So very, very, very different kinetics of response. Far, far less insulin involved in the mouse, even when we're doing it orally, versus the human, bigger glucose excursion. Okay, so conclusions. Unlike in humans, GTTs in mice seem to have a relatively low dependency on insulin, and in some cases they may be completely independent of insulin at low glucose doses when administered by IP injection. At higher doses of glucose, insulin can be measured, and a surrogate of its action can be confirmed that it is impacting on WAT. It's doing something. So GTTs suffer from massive batch effects. They're also susceptible to operator errors. And so I would argue care must really be taken in relating any changes in glucose tolerance to indicate alterations in insulin sensitivity. You have to be very, very careful with that as a conclusion. Okay. So we move on to ITTs, insulin tolerance tests, because this is a bit more of a direct measure of insulin sensitivity. So the insulin tolerance test was originally developed as a human diagnostic tool to test hypopituitarism. So if you make someone hypoglycemic, you will be able to observe a rise in growth hormone and cortisol if you can get their blood glucose below 2.2 millimoles. So that's generally considered to be the point at which you start to see these counter-regulatory responses. It is an extremely risky test, as if the blood glucose falls too low and the insulin is put in IV in this test, it is possible to cause a diabetic coma, and then you have to rectify that with intravenous glucose. In mice, we use this test to try and assess insulin sensitivity. And here is an ITT. So we put the insulin at time 0, generally because of that stress response that I showed you in the hepatic glucose levels during a GTT. You don't get a huge drop at 10 minutes. You'll sometimes see some drop. Sometimes you'll even see a little increase like the yellow dots. And then you'll see a big fall by 30 minutes and it levels out. However, one of the biggest problems with ITTs, this is quite a nice test, is that insulin has a really narrow effective range. And if you have too little insulin, you get no effect. So this is actually an ITT. It looks a bit more like a GTT than an ITT. This was male mice on a chow diet, and they were injected with 0.66 units per kilogram. And you actually see an injection stress effect, and then really you get almost no drop below baseline in this group of animals. The problem is you can have at exactly the same dose, 0.66 units per kilo. In this case, we were looking at a female mouse on a 60% high-fat diet. So that should have actually caused a decent amount of insulin resistance. So this isn't a particularly strong dose. What we see in this one particular mouse was a spectacular drop in the blood glucose levels. And so at 30 minutes, it got down to 2.5. And so we were actually required to do an additional measurement under our license 10 minutes later, because normally we wouldn't take a 40-minute measurement. And at this point, it had reached 1.8. It had not started to rectify. So then we inject glucose. And that's why we see a sudden jump up. And so we saved this mouse, which was good. But the key point I want to show you here is the somewhat sigmoidal relationship in the dots. So it doesn't fall in a kind of a bolt linear point, it starts to flatten out. And the reason in part it's starting to flatten out, partly enzymatic kinetics, you've got less blood to dispose. So, but the second key point is this, counter-regulatory responses. If your blood glucose falls really low, you will get stress hormones, such as, we've already mentioned cortisol, we've already mentioned growth hormone, but you will also get things like catecholamines, which will promote the release of glucose from the liver. And you will also get glucagon being produced, which is again going to promote the release of glucose from the liver to counteract the effects of this hyperglycemia. And so in this case, we can see the counter-regulatory responses kicking in because we've made this mouse profoundly hypoglycemic, but they kick in at somewhere between 4 and 5 millimoles per liter, it's believed, in mice. And so if you have a whole group of animals where you've used a little bit too much insulin, not to the extent that we have a mouse going hypoglycemic, but just a bit too much. And it looks like a very nice ITT. Actually, when we get here, you're getting into the area where counter-regulatory responses are kicking in. And so that's one of the problems with it. We are no longer at this point assessing insulin sensitivity. We're assessing the ability of the mouse to mount a counter-regulatory response. So how do we actually analyze an ITT? And you could sort of ask the same question for a GTT. I think the ITT, though, is actually slightly more problematic, so we're focusing on here. Well, one thing you can do is take this sort of area, this area of curve, and say, the insulin that I injected in my mouse was able to lower this much glucose by time. So this area. And therefore, obviously, the bigger your area is, the more insulin sensitive the mouse, because we can also see the yellow ones where the equivalent area is shown here in blue. And you can see the red area is much bigger than the blue area. And so you can take that AOC, and the nice thing is it reduces your 7 data points, which are a repeated measure in your ITT, down to just a single data point, an area of curve. And so that's great. And if you analyze it for these two groups of animals, you do indeed see a significant worsening of the ability of insulin to reduce glucose in the yellow rather than the gray mice. However, there's another argument that says the half-life of insulin is only about 4 minutes. So after 30 minutes, you'll have done 7 half-lives. So you'll only have about 1% of the insulin you injected. Obviously, you also have the speed of absorption to factor in, but you could argue that the more important aspect to look at is not the sort of area out here where you may have counter-regulatory responses kicking in and the mouse trying to rectify its blood glucose, but simply look at the suddenness of the drop as an acute effect of insulin action. And if you do this, what you can see is the reduction in glucose between 0 minutes and 30 minutes, just simply subtract the 30-minute glucose value from the 0 minute, you get an even more spectacular effect than using the AOCs. So I would conclude by saying the ITT is a more direct measure of insulin sensitivity than the GTT. Which components of the ITT you use for assessment of essentially what you say is insulin sensitivity radically alter the magnitude of the result. So if you're using AOC versus 0 versus 30-minute glucose levels, you're going to get a different result. So I would also say probably the single critical technical point is getting the dose of insulin right. So you've got to take really great care to make sure that the insulin dose you're using does not cause hypoglycemia and also doesn't cause sort of the more subtle effect of dropping into the counter-regulatory zone. But you also need to have enough to actually see any effect at all. And so that's one of the critical aspects. So I would always suggest a bit of a pilot if you're doing ITTs on mouse lines you haven't used before. Okay, moving on to the final sort of large section of this talk, and then we've got a couple of tiny bits at the end, which is clamps. So euglycemic hyperinsulinemic clamps are often described as the gold standard method for measuring insulin sensitivity. And there are various different kinds of clamp which can give you different information, but for insulin sensitivity, the most common method is the euglycemic hyperinsulinemic method. And so in this method, we try to maintain our mouse at the same blood glucose throughout the experiment, and that could be a fixed value. People often use 8 millimoles per liter in C57 Black 6s, but you could also just clamp them to their starting glucose. But it's meant to be a roughly physiological blood glucose level, not a hyperinsulinemic level or a hypoglycemic or hyperglycemic method. And those clamps can be used for other purposes. So the way the experiment works is we infuse insulin, which we would normally expect to lower blood glucose. And in fact, we may infuse enough insulin that if it was uncorrected, we would kill our mouse. But in order to prevent blood glucose dropping, we also infuse glucose to maintain euglycemia. And because we're generally using quite a large dose of insulin, we largely remove the impact of the pancreas. So with our GTTs that we do with an oral GTT, how well the beta cells can secrete insulin can actually impact on our blood glucose. In this case, we're getting rid of the pancreas out of the situation. And we can select which dose of insulin we want to use. So we have a huge amount of control over which aspects of insulin sensitivity we are assessing. So I would argue, and I think most people would argue in the field, it's a cleaner assay than a glucose tolerance test or an ITT, as many of the variables are controlled. Like we don't we're going to be at 8 millimoles, for example, of glucose in the blood, so we're not going to get counter-regulatory effects in this setting because the glucose never goes low enough. So therefore, it's potentially more powerful because of all this control we have over it. And as a result of this, we often see really quite spectacularly larger effect sizes with clamps. So we've seen this with quite a lot of models than we do with GTTs and ITTs. So this is just showing some data from a paper from last year we published working in collaboration with Lazarus Fuchs. And it was looking at an adipose tissue-specific deletion of P110 alpha. Okay, so part of a PI3 kinase complex. And we deleted P110 alpha, and you can see the ITTs here. They're a bit different, which is nice. The knockout is showing a little bit of an effect here. The GTTs, absolutely identical. But then when we clamped these mice, we could genotype the mice off their glucose infusion rate. So if your mouse is more insulin sensitive, you need more glucose for the same dose of insulin in order to maintain blood glucose at that, say, 8 millimoles. So if you're hypersensitive and you're putting in, I don't know, 4 units per hour per kilogram of insulin into a wild type mouse, and it's nice and insulin sensitive, you're gonna need to pump a lot of glucose in to avoid its glucose levels dropping. If you're insulin resistant, on the other hand, you might only need a small amount of glucose to maintain euglycemia. And so this is the glucose infusion rate, the glucose we're infusing, and you can see the blue is the wild types and the red is the P110 alpha knockouts. So it's in the paper as well. It's a bar chart in the paper, and whereas this is just showing it over time. And so you can see these differentials in ITTs and GTTs become this in the context of a clamp, where we can select very specifically insulin doses, and we can control a lot of the variables that can muck about with ITTs and GTTs. And so I've already kind of gone over it, but just to formally sort of show you in concept, what we're aiming to do for time, this is the time of our experiment, what we're aiming to do is keep the blood glucose of our mouse completely static. Now in the basal state, before we've got any insulin in, all of that blood glucose has been contributed by the liver and to an extent a little bit the kidneys, but we mainly think of it as liver. However, as soon as we start to put insulin in, the contribution of the liver will fall because insulin will suppress glucose production by the liver. If we want to keep our blood glucose of the mouse constant, we replace it with our glucose infusion rate, and then the blue and the red lines add up to the black. And again, the more insulin sensitive your mouse is, then the more the red line will drop and the more the blue line will need to go up. In other words, you will need to infuse more glucose. So some clamping terminology, I should have probably put this slide like 3 slides ago. So GIR is glucose infusion rate. That's how much glucose do you have to infuse to correct the effect of the insulin you're infusing. RD, that's the rate of disposal or disappearance. That's how much glucose is being taken up by your periphery, by your muscles, your heart, your brown fat. RA is the rate of appearance. That's how much glucose is being produced from the liver, for example, and the kidneys. And HGP is the hepatic glucose production. And that can be equivalent to the RA in the fasted state. Okay, so a lot of people focus with clamps on tracers, but you don't actually need a tracer for a clamp to be hugely powerful. We saw in the earlier slide the GIR differential between the wild type and the P110 alphas versus the effects in the GTT and the ITT. And I would argue that by itself is enough to justify doing a clamp. And indeed, if you just have a significant difference in GIR, you can say that in this case, drug X made animals more insulin sensitive than saline. But what do tracers allow us to do? So without the tracers, we can only assess the GIR, and this will tell us whether our mice are insulin sensitive or insulin resistant, but it does not tell us if the mouse is insulin resistant in the liver, the muscle, or the adipose tissue. And if we want to determine muscle and liver insulin sensitivity, split that GIR differential into tissue-specific sensitivity, we need to be able to measure the rate of glucose disposal into organs like the muscle, and also the amount of hepatic glucose production of the mouse during both basal and the clamp stage. And we can do this by using a single tracer where we just label glucose, normal glucose. So what properties should a tracer possess? This is just a general point about tracer. Ideally, it should be metabolized in a manner that is biologically identical to the endogenous tracee. So that's usually pretty straightforward with glucose tracers. And in the case of glucose metabolism, it should be irreversible. So there is capacity for glucose to go through quite a lot of futile cycles. And if you have a tracer, you want it to be an irreversible destruction when it takes it up at the level that's appropriate, essentially. So it should not be possible to reform or recycle. Okay. So this is how tracing works in the context of clamps. So we've got our blood glucose levels. We saw this earlier with our model of the GTT. We have hepatic glucose production in the fasted state. That is providing the glucose in the bloodstream, and then the RD is the removal. So if HGP equals RD, then blood glucose will be stable. HGP is greater than RD, blood glucose goes up until we find a new steady state. And the converse of HGP is less than RD, then blood glucose will go down until we reach a new steady state. So if we want to measure the RD and the HGP, this is how we can do it. So we can infuse a tracer, and we infuse it via the tail vein in the experiments we do. And this tracer will mix with the glucose in the mouse's blood, and it will be diluted. So the tracer that we're infusing is at 100%. Obviously, when it hits the blood, it will mix with the mouse's own unlabeled glucose in red, and therefore we will have a mixture. And in terms of the maths, what we're going to say, basically look at is how much does this tracer get diluted? Because the more it gets diluted, it means the bigger the HGP is and the bigger the RD is. So it's the concentration of tracer in the infusion divided by the concentration of tracer in the blood. So if our tracer gets diluted 10 times, so the concentration of our infusate, say, for example, is 100 nanomoles, and in the blood, it's 10 nanomoles, that means that the amount of HGP is going to be 10 times what we're seeing in the infusate, because it's been diluted tenfold. 10 times more is coming from the liver than is going in through the tail vein. So we take essentially this dilution coefficient, and we multiply it by the rate of tracer infusion, and we get the RD. So RD minus tracer infusion gives us our HGP. So we can see, and we can see it nice and visually here. We have 10 circles here. One of them is yellow because it's coming from the tracer. As we've got one yellow going in the tail vein, we must have 9 coming out the liver in order for this to all balance up nicely. And the key point here is that you have to have a steady state for this mass to work. So when you initially start infusing your tracer, it's going to take time for it to build up in the blood of the mouse. And in our sort of practical experience, we think you need to infuse a tracer for about 90 minutes, something like 90 minutes to get a nice steady state. If you look at, say, 20, 30, 40, 50 minutes, you'll see steadily higher and higher levels of the tracer building up in the blood as everything mixes nicely and comes to equilibrium. So what happens when we put insulin in the system? Well, insulin does insulin-y things. It reduces the amount of glucose being produced by the liver, and it promotes the uptake of glucose by the muscle. So the RD goes up. So we've gone from 10 circles to 25 here, and we've gone from 10 9 circles here for the HGP down to 2. Obviously, you can see that 1 tracer and 2 HGP do not match 25 for the RD. So obviously the glucose would begin to diminish over time. But what we do is we replace the missing 22 balls of glucose by infusing it into the mouse. And again, we do this via the tail vein. And so we then have the glucose infusion rate, in our case, 22 units of glucose here. We have 25 units of glucose being disposed, 2 units of hepatic glucose production, and 1 unit of tracer. And one consequences of this is if this glucose is all unlabeled, then the tracer will be substantively diluted in the blood. In fact, we have only 1 yellow circle here, whereas previously we had 3. So The RD equation remains identical. The concentration of tracer in the infusion divided by the concentration of tracer in the blood times the rate of tracer infusion equals RD. And if we've kept the tracer infusion equal and and kept the blood glucose constant, and we assume the blood volume is relatively similar, well, the only thing that's changed in our equation from the basal state is this concentration of tracer in blood has gone down threefold. And because this is the denominator, this means that this section will have got larger and will have a bigger RD. And that's indeed what we see, 25 versus 10. RD minus the tracer infusion minus the GIR, so 25 minus 1, so that's 24, minus 22, I think that's right, 22, gives us 2. So that's the HGP. So 25 minus 22 minus 1, 2. That's the HGP. So that's how we can calculate the hepatic glucose production. And just a note here when you're looking in the literature, HGP plus GIR plus tracer infusion, if relevant, must equal the RD. It's a simple mathematical sum. If you ever are looking at clamp data and the HGP and the GIR clearly do not add up to the RD in the clamp stage, there is something wrong with the maths, because it's very, very simple, assuming they're using steady state kinetics. So just to reiterate this point, the lower the tracer concentration in blood, the greater the RD. And so this is the data we end up with. We'll end up with some data from the basal state, and in the basal state, the RA and the RD are basically equivalent. And in this set of data, it's about 1.3 micromoles per minute per mouse. We then will have the clamp RD, which in this case has gone up about threefold. We have the GIR, so most of this induction is being accounted for by our glucose infusion, and we have the hepatic glucose production in the clamp phase. Okay? Now, this increase in RD is a measure of peripheral or muscle insulin sensitivity, whereas this suppression of HGP, so it's lower in the clamp phase than it is in the basal state, the suppression of HGP is a marker of liver sensitivity, and in the basal state, basal RA is essentially equal to basal HGP. We can also measure the insulin in the blood to get an idea of how strong our hyperinsulinemic component was. And so in this experiment, we trebled insulin levels, so that's pretty punchy. And of course, these were maintained constantly at high insulin levels, and they're going in IV. And then we also can measure the ability of insulin in the setting to suppress free fatty acids, and they get powerfully suppressed in serum. So we go from about 1100 micromoles in the fasted state, it's a fairly standard value in the fasted state, and then under the full clamp setting, we drop down to about 300 to 400 micromoles. So we've about threefold reduction in free fatty acids. And so this is a surrogate for adipose tissue insulin sensitivity, as the action on AT is to suppress free fatty acids. If you have adipose tissue insulin resistance, then this suppression will be less. And the reason being able to measure these things is important is because we may need to select our insulin dose based on it. So the effect of insulin on different organs is not uniform. So insulin concentration is, what you will find is that the effect of insulin will max out at a lower concentration for liver and adipose tissue than for muscle. At least in humans, this is true. So if you had an insulin concentration of, say, 6 units per kilo, you would expect to see 50% of insulin's effect on muscle, and you would expect to see 100% of insulin's effect on liver and adipose tissue. Conversely, at just 2 units, what you may be seeing is about 50% of insulin's effect on liver and adipose tissue, and absolutely no effect whatsoever on muscle. And that is the case. We do see experiments where we see between the basal and the hyperinsulinemic state, we see absolutely no effect on RD, but we still have a GIR component because all we're doing is suppressing hepatic glucose production. So different organs have different dose effects. Okay, so I'll conclude this section by saying clamping is the gold standard technique for assessing insulin sensitivity. And I've not gone into too much detail, and I'm not going to do too much now, but to say that the tracers that we've been talking about, you can either use stable tracers or you can use radioactive tracers. And so main advantages of stable tracers is you don't need to use radiation, which reduces the paperwork. They're cheaper. You can get Keith Burling and CBAL or any other kind of biochemistry core to measure things like free fatty acids and insulin. If you're using radiation, you're going to have to do it yourself in a radioactive lab. The big one is you get tissues out at the end, which aren't radioactive, so you can do molecular analyses on them. Whereas with radioactive tracers, the really big advantage is the capacity to use deoxyglucose for tissue-specific uptake, and I've not covered that today. It also has an advantage that you're using it at true tracer levels. So when we use stable glucose, for example, we may be putting in as much as 10% of the mouse's blood glucose turnover. With radiation, it will be sub 0.1% because radiation is so much more sensitive than stable isotopic measures. And just to show that advantage of being able, using stables to get your tissues at the end, I'm going to show something here, which is a correlation between GLUT4 expression in white adipose tissue and RD of the whole mouse. And so adipose tissue insulin sensitivity is assessed by GLUT4 expression, correlates with the whole body insulin sensitivity. So there is a New England Journal of Medicine paper from, I think, nearly 20 years ago where Pete Shepard and Barbara Kahn said GLUT4 mRNA expression in white fat is an excellent marker of whole organism insulin sensitivity. And this shows pretty much what I've always found, which is that statement seems to be very true. It doesn't hold true for muscle mRNA expression of GLUT4, but it does seem to be true of white adipose tissue. And you can't do this with radiation unless you want to fill out a lot of risk assessments to allow you to extract RNA from radioactive tissue. Okay, so we go about, so in conclusion, we've got clamping is the gold standard technique for assessing insulin sensitivity. You need to select your insulin dose to study the specific aspect of insulin sensitivity you're most interested in. Are you most interested in adipose tissue and liver or muscle? And stable and radioactive isotopes can give us more information than just glucose infusion rate, and each has advantages and disadvantages. All right, so we've got about 4 slides left, I think, 5 slides left. So I'm just going to quickly go through these just to show them. Lipid tolerance tests. So I showed the data earlier from the GTTs on this paper, from this paper, but there's a really important point about PPAR gamma 2. It's an adipose tissue transcription factor that's super important for controlling lipid storage. So whereas adipose tissue really doesn't do a lot in terms of mass action, it doesn't actually take up that much glucose. So we've looked at the GTTs, which were interesting in the fed state, perfectly normal in the fasted state. What about the lipid tolerance tests? Well, we see a huge difference between lipid tolerance test on the right here and glucose tolerance test on the left. And in principle, they're almost exactly the same test. You replace the glucose from a GTT with lipids, and in this case, we used olive oil, but different lipids may give different results. We haven't done a lot of work looking into that. And this one is 200 microliters of olive oil orally. 2 things to note, and these are really the only 2 points I'm going to make. First of all, obviously you are measuring different things. In a GTT, you're measuring glucose. In a lipid tolerance test, you're measuring triglyceride. So practically, you're going to have to collect serum, and then you're going to have to biochemically analyze the TG after the fact, so you won't get your data out at the same time. And the other is the timescales. GTT, 120 minutes. LTT, this is 8 hours. So you've got very, very different timescales for these tests. So I would argue in conclusion, if your model is one where you're primarily targeting adipose tissue, then given adipose tissue's function is to take up and release lipid, an LTT might be a more suitable test to start with than a GTT. And it is based on the data I've just shown you, you can have a spectacular impairment in lipid tolerance without an alteration in glucose tolerance. One sort of minor technical note is that this can be affected by gut absorption of lipid, obviously, but usually this is really relevant if your LTT is improved, i.e. if you have less of an excursion, because in wild-type mice, lipid absorption is pretty good. So it's very unlikely that you will get a massive impairment or a massively bigger LTT like this one. That's not going to be caused by a huge increase in lipid uptake from the gut. There just isn't enough headspace. But a reduction, so a flatter line than this black one, could reasonably be explained by a problem in gut. The final technique is the simplest. This is acute insulin stimulation for analysis of phosphoproteins. So in this protocol, what they did was took some mice, fasted them overnight, and injected them with 2.5 units per kilogram of insulin. Now that is a lethal dose, so we have to kill the mice before the insulin does. So I killed the mice 10 minutes later, and then I harvested the tissues rapidly. So under 2 minutes, I had them into liquid nitrogen for snap freezing them. And so the following Western blot shows EWAC from a level 6 knockout mice. These are males, they're 8 months old. So what we see here is control versus insulin stimulated, and we're looking at phospho-AKT, phosphorate on the serine 473, I think it is. I don't think it's 474, versus total AKT. And so it essentially shows that you take a fasted animal here, inject it with insulin, and you get a massive induction in measurable of AKT phosphorylation. And the knockouts were somewhat reduced. So it looks nice. I think they're very attractive plots, but it's actually practically important because it's quite hard to assay, for example, for different WAC depots, 2-deoxyglucose disposal, which is a tracer that you can use to look at glucose uptake because they have such low glucose uptake relative to the mass of the tissue. So it can be quite a nice technique for looking at, and also for looking at downstream events, signaling events from insulin. Okay, so I'm going to conclude there. So I would say that this has been a general introduction to some of the most common metabolic tests for looking at insulin sensitivity in rodents. There is a huge amount more out there in the literature. I mean, there are papers and papers and papers looking at GTTs, looking at ITTs, and if you're particularly interested in these techniques, I would certainly recommend going and having a looking at them. But there is one very important take-home message, I would argue, from all of these. Given how long we have spent discussing the niceties of the GTT, even if a test seems simple, don't assume that it actually is in practice. Okay, so thank you very much, and that's the end of today's talk.